Hello, AP Computer Science. Today I'm going to try and teach you about relatively simple instances of recursion. Now, recursion is you've got a function that calls itself on a smaller version of itself to solve a bigger problem. Now, you use recursion on problems where you can break into smaller subproblems, such as factorial. Factorial is an excellent example. The key to this is you need a base case. Base case is some situation you know, so you don't have to keep calling it on a smaller version of itself at that point. Once it hits the small base case, we can just return a number. And you got to be able to have some way of taking the bigger problem and like solving a little part of it and then adding that in some way to a smaller subproblem. So let's take a look. I'll do a bunch of examples. I've got 5 in mind. First one is factorial. Very common example. It's the thing with the exclamation point. So 5 factorial is 1 times 2 times 3 times 4 times 5. 0 factorial is defined as 1. 6 factorial would be 1 times 2 times 3 times 4 times 5 times 6. So let's do this with recursion. I know you could easily do it with a loop, but let's just try recursion because it's very useful for a lot of things. So first thing you probably want to put in is your base case. If n equals 0, I know that 0 factorial is defined as 1. So I'll just return 1. That's my base case. The way I'm going to reduce my problem is call it under a smaller number. And so if I'm not at 0, I'm going to return whatever n is times whatever factorial of one smaller number is. So 5 factorial is 5 times 4 factorial. 4 factorial is 4 times 3 factorial. 3 factorial is 3 times 2 factorial. And so this will do it. We got our little base case. We got a way of breaking a bigger problem into one little part times a smaller subproblem. And you notice we got it all right. So that's good. There's one. Let's try some more examples. Next one, a very common example is Fibonacci. By the way, this is a very inefficient way of doing it. Someday you'll probably learn something called memoization, which is a much more efficient way to do this, but if you're working on small numbers, this will work great. So the Fibonacci sequence, basically Fibonacci of 0 is defined as 0, Fibonacci of 1 is defined as 1, and then you can build from there. So let's do our base cases. So if n equals 0, we're just going to return 0 because we know what that is. And if n equals 1, we will return 1. So we've handled our base cases. And our strategy is the Fibonacci numbers. Each number is equal to the previous 2 numbers added together. So the third Fibonacci number is equal to the first Fibonacci number plus the second Fibonacci number. The fifth Fibonacci number is equal to the fourth Fibonacci number plus the third. So each number is equal to the sum of the previous 2. So 5 is equal to 2 plus 3, 8 is equal to 3 plus 5, 13 is equal to 5 plus 8, 21 is equal to 8 plus 13, and so on. So that's Fibonacci. So once we've got our base cases handled, so we don't keep calling it on smaller subproblems forever and going into negatives, what we're going to do is we're going to turn any Fibonacci number is just equal to the previous Fibonacci number plus the one before that. And that's it. So we broke our big problem into smaller subproblems. And then this guy, like let's say we did the fifth Fibonacci number. That would equal the fourth Fibonacci number plus the third Fibonacci number. And so The fourth would be if n was 4, it'd be equal to the fourth plus the third, the third plus the second. The third would equal the second plus the first. The first would return right away. The second Fibonacci number would be equal to 0 plus 1, so it would also be 1. Anyway, just imagine subbing in the number for the function. So if you put in 5, it'd be like, okay, it's not 0, it's not 1. I'm gonna call it on 4, and I'm gonna call it on 3. And so then if this was 4, it'd be like, hey, it's not 0 and 1. I'm gonna call it on 3, and I'm gonna call it on 2. And then let's say it was 3. Hey, 3 is not 0, it's not 1. I'm going to call it on 2, and I'm going to call it on 1. 1 can return right away. 2, it would have to get called again. 2 is not 0, it's not 1. But 2 would be called on 1 and 0, so it would be 0 plus 1. 0 plus 1 is 1, so the second Fibonacci number would be 1. And then you'd keep building up from there. Once you can finally return a number, it would just keep coming back. All right, so these are the 2 common examples. Let's get into some other ones with the same idea. Let's do count x. So really, we just want to count the number of lowercase x characters in the string. So I'm going to say my base case is I have an empty string. If I have an empty string, I know I can just return 0. String dot length, if that is equal to 0, or I could just say if the string is equal to the empty string, I'm just going to return 0 and just done. So that's my base case. Aside from that, I'm going to, if string dot char at 0, if my first character is equal to an x, I will return 1 plus count x on a substring starting at 1. So basically, if I see an x, I'm going to return as the first character, my count will be 1 plus whatever the count is for the rest of the string. Or if it's not an x, I will just return whatever the count is for the rest of the string, because I get 0 for that particular letter, for the first letter. And so that would do it. Oh, as long as I remember my end bracket. Oop, just sucking today. Error. So it kind of makes sense. We got our base case. Once it hits 0 things in it, we just return 0. Aside from that, if our first character is an x, we return 1 plus the count for the rest of the string. Or if it's not an x, we just return the count for the rest of the string. And that will effectively count up all our x's. I also wanted to do no x. So this is messing with the string. So in this one, I want to compute recursively a new string where all the x characters have been taken out. So here we go. The base case would probably also be an empty string. Might say string dot length equals 0. I will just return the string. Otherwise, if I'll just do it a character at a time, starting from the first character. If the first character is equal to an x, I'm just going to return no x of the rest of the string. Oops. Because that well, I didn't include the x, and I'll do the rest of the string. Otherwise, if there is an x, I will return that character. Maybe I'll use substring so I don't get any weird errors. So I'll return the first character plus the results of calling no x on the rest of the string. So we build up the string a character at a time, and that should do it. Sweet, we got them all. All right, so again, we got our base case, the thing that deals it in our smallest possible case, and then we do a bit of logic on is the first character on x, and that's all we have to do with. If it's not an x, we include the character, and then we just do no x on the rest of the string to do its logic. Otherwise, we don't include the first character because we're not supposed to include x's, and we just call no x on the rest of the string. So yeah, this whole breaking into smaller subproblems. I only have to think about a little bit at a time. One last example. I know this is a long video. Apologies for that. Let's do array 11 because I want to do an array 1. Now this guy, it takes two inputs. It takes nums and it takes an index, what index we're currently at. And all we're supposed to do is count the number of times that we see 11. So let's think of our base case. What's our base case? If our index is equal to the length of the string, we could do greater than equal just to be safe. If it is greater than or equal to nums.length, we've gone too far. We will return 0. There's definitely no more 11s. Otherwise, we'll look at the current index and check to see if it's an 11. And if so, we'll return 1 plus it. So we have our base case. Here's our sub logic. If the number at the index, if nums index, if that is equal to 11, we will return 1 because we found 11 plus the result of array 11, our function, on the same array, but index plus 1. And then if we don't see an 11, we will just return array 11 on the rest of it. It's basically returning 0 plus the result of array 11 on the rest of the array. And if we go try that out, theoretically, we're good to go. Perfect. So you notice it can be pretty hard to figure out the logic sometimes, particularly in some of the harder AP questions, but the basic idea isn't that terrible. You need a base case to handle the really small case that you know that you'll end up in, guaranteed. You need to make sure that at some point your base case triggers, otherwise you'll get a stack overflow error. It basically keeps doing recursion forever. So make sure you do end up hitting a base case at some point. And then you need some small little bit of logic which lets you break down the problem. So you do a little bit of it and then can call itself on a smaller subproblem. That is recursion basics. I'll go over some of the harder problems next video. Be well.